The first thing we're asked to find in this problem is the current in each of the branches. I'll assume each of those currents is directed to the left and label them I1, I2, and I3. To solve for these three unknowns, we'll need three equations. To get those, I'll use two Kirchhoff loop rules and one Kirchhoff's node rule. The first loop rule will be for this loop at the top, the second one for this lower loop, and for the node rule, I'll use this node that I'll indicate in blue. If we apply Kirchhoff's loop rule to the top loop, we can start at the 10-volt battery to have 10 volts minus the voltage drop across the 2 ohm resistor, and then a positive sign as we move against the assumed direction of I2 through the 1 ohm resistor, another minus sign as we move from positive to negative through the 5-volt battery, a positive sign as we move against the assumed direction of I2 through the 4 ohm resistor, and finally a negative sign as we move with the assumed direction of I1 through the 3 ohm resistor. All of those voltage changes sum to 0. Let me just quickly note that I'm dropping all the trailing zeros for compactness. We'll assume three significant figures throughout. Collecting like terms gives us this expression. After dividing by 5 ohms, we find that I1 minus I2 equals 1 amp. I'll underline that in green and call it equation 1. When we write Kirchhoff's loop rule for the second loop, starting at the 5-volt battery, we find 5 volts minus the current times the 1 ohm moving with the direction of I2, and then a plus sign as we move against the assumed direction of I3 through the 10 ohm resistor, and then a minus sign moving in the assumed direction of I2 through the 4 ohm resistor, and all those sum to 0. We again collect like terms and divide by 5 ohms to find that I2 minus 2I3 equals 1 amp. I'll underline that in green and call it equation 2. Now for the node rule applied to the blue node, summing all of the currents, setting it equal to 0, we see that currents I1, 2, and 3 are all directed towards the node, so they all have a positive sign. That gives us equation 3. Now we need to solve these three equations for three unknowns. There are many ways of doing this. I'll show you one. I'll start by rewriting those three equations. And then multiplying the third one by 2 and adding all three equations together. The I3 term then disappears, giving us 3I1 plus 2I2 equaling 2 amps. From equation 1, we know that I2 equals I1 minus 1 amp. We substitute that into this result, giving us this expression, which we can simplify and solve for current I1. This shows us that I1 equals 0.8 amps. Now that we know I1, we can substitute that value into the first equation, I1 minus I2 equals 1 amp, and solve for I2. That works out to negative 0.2 amps. The negative sign here tells us that the direction of I2 is opposite the assumed direction. I2 is directed to the right, not the left. Knowing I1 and I2, we can then substitute into the other equations. I chose equation 3, so I1 plus I2 plus I3 equals 0, which tells us that I3 equals negative 0.6 amps. Again, the negative sign tells us the current is against the assumed direction. Current I3 is also directed to the right. Part B asks us for VAB, the voltage at point A relative to point B. To find that, we'll use this partial loop that I'll draw in orange. Starting at point A, we have the voltage at point A plus, as we move against the assumed direction of I1 through the 3 ohm resistor, minus, moving with the assumed direction of I2 through the 4 ohm resistor, equaling the voltage at B. Substitute the currents from the previous step and calculate to find that VAB is negative 3.20 volts. The voltage at A is lower than the voltage at B by 3.20 volts.